All right, so let's work on this problem. This is a little distracting if you look at all these bits and pieces, but really this is just a simple roller support at A and a pin at B. It's basically a simple supporting beam. So the problem wants to know what's the maximum positive moment at C and the maximum positive shear at C for a uniform dead load and a single live load. Okay? So the first thing we need to do is draw the influence line for moment at C and then shear at C. So we'll do the moment part first, part A. So you might recall that our strategy is to come to C and put in our momentless connection, which would be a hinge. At A we have a roller support, and at B we have a pin. And then come back and imagine positive bending moment on both sides. And that should help us with the shape of the curve. So how's this point going to move? Up or down? Mr. Yang, you know what it's going to do. Up. You're not Mr. Yang.
No.
You're close to Mr. Yang. Yeah, it's going to go up. So then the shape of the influence line should look like this. Okay? So really, all I need to know is this value right there. And that position means that my unit load moving across the beam is at C. I want to know the moment at C. So the way we've been solving these problems is we come back, we draw the structure, we put our unit load at C, and I'm looking at reactions at A and reactions at B. And don't forget, this is the point C. And I'll go ahead and put those dimensions in here. This is 1 meter and 3 meters. So I'm going to eventually come back and I'm going to cut the structure here at C. You guys want to work the left side or the right side? Left? Okay, so that means we need to know the reaction at A. So let's find the reaction at A first. In this problem, the easiest way to do that is just to sum moments at B. So we'll do that. We'll use right-hand rule for our sign convention. We'll make sure it's equal to 0. That'll tell us it's equilibrium. So about B, my unit load at 1 creates what kind of moment? Positive or negative? Positive. It has a moment arm of 3 meters. Then the reaction at AY creates negative moment and has a moment arm of 4 meters. So my reaction at Y is 3/4. So then I can cut the structure at C, put my AY reaction on, which is 3/4, and I'm looking at the internal moment there, the moment at C. That little section from A to C is just 1 meter long. So now I can sum moments one more time, but this time I'm going to sum it at the cut that I made, the section. Make sure this free body is in equilibrium. So this moment that I've assumed, positive bending moment, with my sign convention is positive. The reaction is going to create negative moment. So the force is 3/4 and the distance is 1 meter. So it looks like MC is going to be 3/4 of a meter. So now I can come back and draw my moment at C diagram. We already know the shape. It's going to look like this triangle. And now we've just found out the value. This is 3/4. And all these values will be in meters, and we know these dimensions are 1 meter and 3 meters. So there's my influence line for the moment at C. Okay? What about the influence line for the shear at C? So this is moment at C. What about shear at C? Well, I'll look at my drawing again. It's still a roller at A and a pin at B. But now I'm going to put this strange shearless connection at C, right? And I'm going to apply positive shear on the left side and positive shear on the right side. So how's this going to move? Well, the left side is going to do what? It's going to go down or up? It's going to go down. What's going to happen on the right side? Up or down? It's going to go up. So there's the shape of the influence line. So now I can quantify that this way. So now the shear at C is going to look like this. We just drew the shape. By the way, these lines have the same slope. And we know that this is 1 meter and this is 3 meters. So how do we figure out these heights here? I know the difference is 1. Now this side is 1 and this side is 3. So this side is 3 times bigger than this side. So that means this value is 3 times bigger than that value. You see that? So let me just call this, maybe I just call this H. So what would this side have to be? This side would have to be 3 times H. 3H plus H equals, has to be 1. So H is a quarter. So this bottom becomes, and it's negative, so it would become negative 1/4. And the top would be 3/4. See that? No real, you have to draw any 3-body diagrams for that. So there's my influence line for the moment at C, and there's my influence line for the shear at C. Now if I want to find the maximum positive moment at C, well, first of all, if you look at the whole structure, it's all positive. So you're going to get nothing but positive moment. There's no loading that I can put on here that would cause a negative moment unless the loading was what? Acting up, right? It's not going to happen. So what's going to happen is we're going to deal with first the dead load. We got a uniform dead load, and then we have this live concentrated load. So let's start with the dead load. It has an intensity of 500 newtons per meter. I'll change that to kilonewtons, so it'll have an intensity of 1/2 kilonewtons per meter. And remember, in all these uniform loads, we multiply it by the total area under the curve, which in this case would be it's a triangle, so 1/2 base, the base is 4 meters, times the height, which is 3/4 of a meter. So what is that? There's 3 divided 3/4. Is that 0.75 kilonewton meters? Hello? Anybody there? I guess not.
0.75.
0.75, thank you. Someone is there. Kilonewton meters. and the live force is 3 kilonewtons. And where are we going to put it to create the maximum influence at C? At C. And that influence is 3/4. So we'll multiply that by 3/4 of a meter. And that will give us 9 divided by 4. That's 2.25. Is that right? I think it is. And of course you add those together and it looks like you get 3. Okay? What if I threw a live uniform load in there? Not in the problem, but I'll do it now. What if I had a live load? And let's say it's the same value as before. Say it's 1/2 kilonewtons per meter. Where do I put the live uniform load to create the maximum moment? Everywhere, right? Because the whole beam is positive. So it would look just like the dead load. It'd be 1/2 the base, which is 4, the height, which is 3/4. And you would get an additional 0.75 kilonewton meter moment. So now what about the shear? Well, let's start with the dead load on the shear. Again, the intensity of that loading is 1/2 kilonewton per meter. What's the total area under the influence line for shear? Well, there's a negative part and a positive part. They're both triangles, so I'll factor out the half. Starting on the left side, I've got a base of 1 meter and a height of -1/4 meter. Then the positive triangle has a base dimension of 3 and a height of 3/4. Looks like a half. Did you get a half?
I got 2.2.
2.2, you forgot this is negative, I think. Because this is 9 force minus a fourth is 8 force. 8 force is 2. Divide 2 by 2, you get 1. Times that should be a half, I think. You got a half? Anybody else get a half? Anybody playing along? Maybe we should start throwing money at you guys to get you to cooperate. Would that be a good thing? Easter's almost here. I'll have a ton of extra candy. Maybe I'll start throwing like Starburst at you or something. I got a reward for participation. No?
Do it.
I don't see anybody getting too upset about that. Maybe I'll do it. All right, what about the live force? We're trying to find the positive shear, right? So where should I apply it? Where's the biggest positive value?
At C.
Yeah, just to the right of C. So I'll apply it there. So that force will be 3 kilonewtons. And I'll apply that at, well, that's funny. They both have the same value. How unusual. Oh, I made a mistake, too. These heights don't have dimensions. Right? On the influence line for shear, it's dimensionless. So the heights have no dimensions. And so you're just going to get a force, kilonewtons. Sorry about that. Well, this is kind of a strange problem because I would never expected it to get exactly the same values, but there it is. So we would add those together and we would have our maximum value would be 2.75 kilonewtons. Now, if I did have a live distributed load, and I'm trying to find the maximum positive value, where would I put that live load? Would I run it across the whole structure? No, I'd only run it over the positive area, which would be from C to B. So in that case, I would have the live load, which is a half or 0.5 kilonewton per meter, and it's still a triangle. But just the positive part would be a base of 3 meters and a height of 3/4. So that's 9 divided by 8 divided by 8. Oh, that's a mess. I don't know what that is. 4, 16, 9/16, whatever that is. 0.5625. Okay? I think that's a reasonable homework problem. And what do you know? We clocked in at 15 minutes and 25 seconds. Right on time.